So today we're zooming through circle theorems. So one circle theorem that's not always thought as a circle theorem is that anything that's got two radiuses, so that's a radius and that's a radius, will always be isosceles because radiuses can't change length, so they'll be the same wherever they are. So that also means that two angles that are suspended in a circle with the centre when two radiuses will be isosceles. So that's how we would write the theorem, but the most important thing to note is that it's isosceles, and that's the key word for when you're doing those proofs. You'll need to state isosceles. Okay, so I know that if this is 112 and we've got a straight line here, so this must be 68. I also know that this whole triangle is 180. So if I do 180, subtract 68, that tells me that the rest of those two angles equals 112. So I've got two lots of x, because this must be x as well, because using that theorem from before, these two are the same, they're both radiuses, so 2x equals 112. So one of those is 56. So I know that x is 56 from that. On to our next theorem. So very similarly, it's not necessarily an isosceles triangle anymore, but if you've got two tangents, then they will be the same length when they meet. So from the point that they are at the circle to the point where they meet, they will always be the same distance. So we've got those two radiuses again. We can see the radiuses must be the same, but the tangents are also the same. So that is our next theorem. So our next theorem after that is that any angle where we've got a diameter, so this is a diameter, we can see it goes from side to side and it goes through the centre, which is important to note. The diameter must go through the centre, and anything that has a diameter is a semicircle, so any angle in a semicircle is right angled. You could also say that an angle with a triangle with a diameter has got a 90-degree angle, but if this is the hypotenuse, this is right angled, and they quite like to hide SOHCAHTOA questions within the circle theorem. Our next circle theorem is the cyclic quadrilateral. So this is a big key word. If you don't call it a cyclic quadrilateral, you will not get the mark for the reason. So opposite angles, so that is this angle is opposite this angle. The same way, this angle is opposite this angle, and they add up to 180. So the two red ones add to 180, the two yellow ones add to 180. And that is our cyclic quadrilateral. Here is our favourite circle theorem. This is the alternate segment theorem. So even if you just state these words here, alternate segment theorem, they would give you the mark. And all that means is that this angle here is the same as this angle here. So the angle between the chord and the tangent is the same as the one that is in the opposite segment, so the one that is not attached to that chord. And this angle here, so the one between the chord and the tangent, is the same as this one over here, and this is one of their favourite theorems to check. So we can just call that the alternate segment theorem. Here is, and I've put both pictures here because lots of people can tell me that the angle at the centre is twice the angle at the circumference, and that is a key word there. But when they draw it like this, this is still an angle at the centre and an angle at the circumference. So again, this one at the centre would be double that one there. But that is your keywords. I tried to already highlight those earlier, but if you do not say centre and you do not say circumference, you will not get the mark. Those are the key words. Don't call it the edge, don't call it the middle, it is the centre and the circumference. This is similar to our other one, but this is same segment theorem. So these two are in the same segment, they are both subtended from A and B. I can see that this one goes back to A and B, so it's ADB and ACB. They both have A and B at the end of them, and they are the same. So same segment theorem are the same. So in the same way, this one down here, DAC, has a D and a C subtending it, and DBC must be the same because they both come from the same points. They both come from D and C. So we should be spotting the cyclic quadrilateral. So I've got 4 points on a circle, so we know it's a cyclic quadrilateral. So we know that these two make 180. So 180 subtract 129 is 51. Woo. So 51, and my reasoning would be opposite angles in a cyclic quadrilateral are 280. Next one. We should spot the two radiuses straight away. So we know both of those are x. So we do 180, subtract 78, which equals 102. And we split that by the 2, so we know 2x is 102. So 1x must be 51. Okay, and that was by two tangents forming radiuses form an isosceles triangle. Okay, again, we can see that this one is at the circumference, this one is at the centre, so we're going to double it, and I'll get 102. And that was by angles at the centre of the circle is twice the angle at the circumference. And then this one, as soon as we're seeing that tangent and that triangle, I know that this one is the same as this one by the alternate segment theorem. But I also know that this is a straight line, so should add up to 180. So 44 plus 85 is 129. So I'm going to do 180, subtract 129, which gives me 51. Because alternate segment theorem and the straight line one. And then our final one, for this one it's a proof, so we're going to need to write it a little bit better, but the first thing I'd be doing on this one is drawing my two lines onto there, and I can very quickly tell you that this one will be 40, so I'm going to write that in words. So QPS, so Q, and I'll just add a little P there, S is 40 degrees, because the angle at the centre is twice the angle at the circumference, or the angle at the circumference is half the angle at the centre. I then know that I've got a triangle there and a chord. So this one is its alternate one. So this is also 40. So QSR is 40 by the alternate segment theorem. I now can see that 40 is the same as 40, so these must be isosceles. So QRS equals QSR equals QRS, which is so it must be an isosceles triangle or isosceles. So this question looks quite complex, and it is. I guess the thing we've got to know is we have got a diameter. So our diameter is here. Oh, where it's squiggly, which means this angle here will be 90. Which if that angle's 90, this angle's 90. So we're using one theorem where we know it's a 90-degree triangle, and then that it's on a straight line. Obviously after that, we can just add and subtract it all from 180. So we can do that bit. Therefore x must be 48, because we've added it all to make the triangle just there. For the last bit for y, that's just up here, and this bit here, y, this is that sneaky alternate segment theorem. So we've got a chord there, alternate segment theorem, yeah. That's a chord, and that's the opposite angle. So actually, those are just equal, so y is 42 by the alternate segment theorem. Okay, so first we need to find angle BFD. The BFD, that's going from here, B, F, and then to D. So that is this angle just there, the angle at F, the angle at the middle. So to find that one, again we've got our alternate segment theorem. So we've got a chord here. So 43 will be the same as 43 by the alternate segment theorem. So we know that that is 43. By the alternate segment theorem. CBD, so CBD. So we know that this is 90 degrees, because that's a radius and a tangent. So if this is 43, then this will be 90 subtract 43, which is 47. By tangents and radiuses meet at right angles. And then the last one, BCD, BCD, that's this angle just here, BCD. So we have got our 59 over here, which is from the B and F, where this one is also from B and F, so this one will also be 59 by the same segment theorem.